Okay, try this. Close your eyes for a second. Picture something incredibly valuable. Right. Say, gold. Lots of it. But it's sitting hundreds of miles beneath your feet. Not, in a mine. Deep, deep inside the Earth, locked away in the planet's molten core.
Right. Seems completely unreachable.
Utterly impossible, yeah. Like a vault sealed since the Earth formed billions of years ago.
And that's basically the picture we've had for a very long time. We think that when Earth formed, maybe 4.5 billion years ago,
Uh-huh.
something like 99.999% of the planet's precious metals, gold, ruthenium, things like that, they sank because they're dense.
Right.
And they ended up right down there in the core, separated from us by, well, the mantle, that huge rocky layer.
Because most of the planet's volume, right? Like 84%?
Exactly. So, yeah, the ultimate inaccessible treasure chest.
Okay, but here's where it gets really kind of mind-bending. What if that core, that vault, it isn't actually sealed? What if, somehow, it's leaking?
Leaking.
That's the core idea, excuse the pun, from some really fascinating new research we're going to deep dive into today. This study is suggesting the core isn't as isolated as we thought,
Okay.
and it's actually like oozing some of that precious material upwards into the mantle.
Wow. Okay, now, we're talking geological time, I assume, not like
Oh, yeah, definitely not cartoon geysers of gold. It's slow.
a very slow ooze, perhaps. But still, the idea that anything is coming out of the core and moving up,
Yeah.
that's big. The evidence must be pretty interesting.
Exactly. So our mission, really, in this deep dive is to unpack this. How did scientists figure this out without, drilling an impossible hole?
Right.
How does this stuff even get towards the surface? And crucially, what does it tell us about what's happening deep, deep down?
The dynamics of the planet.
Yeah, we want to pull out the key insights so you can really grasp this discovery and, frankly, why it changes things. Let's get into it.
All right. And to really get it, like you said, the context is key. That standard model, planet forms, cools, differentiates, then stuff sinks. Iron, nickel. And yeah, most of the gold, the platinum group metals, they go to the core.
Leaving just tiny amounts up here in the mantle and crust.
Tiny amounts, relatively speaking. And for, well, billions of years, the assumption was what's in the core stays in the core. Full stop.
Right. Because getting down there, forget it. Hundreds of miles of solid rock, insane heat, pressure. It's pure science fiction territory.
Completely. So the idea of material coming up from the core, it feels wrong somehow, counterintuitive.
It really does, which is why this study's main finding is potentially such a big deal. It suggests the core isn't a closed box.
There's interaction, some kind of exchange happening at that boundary, the core mantle boundary. Material is crossing over.
Okay. The obvious question then, if you can't go down there and see it,
Yeah.
how did they find evidence for this? Where do you even look?
Yeah, this is where the science gets really clever. It's detective work. They didn't go down. They looked at what comes up to
The
it.
volcanoes.
Exactly.
Yeah.
Specifically samples of volcanic rocks. And not just any volcanic rocks, but ones from places like oceanic islands. Think Hawaii.
Why those specifically?
Because the magma that forms those islands is thought to originate from really deep within the Earth's mantle. Potentially very close to that core mantle boundary.
Okay, so they're like geological messengers.
Yeah.
Bringing stuff up from the depths.
That's a good way to put it, yeah. So they analyze these rocks,
Yeah.
looking for tiny, tiny traces of specific element.
Like the gold.
Well, gold is part of it, but a key element they focused on was ruthenium.
Ruthenium. Okay, why that one?
It's a platinum group metal, chemically similar to platinum, iridium, and gold. And it's one of those elements we strongly expect ended up mostly in the core.
Right.
The real challenge then is telling the difference. Is this tiny bit of ruthenium in the rock something that was always in the mantle, or did it somehow come from the core?
Ah, okay. That's the tricky part. How do you tell them apart?
And that's the breakthrough. Scientists at the University of Göttingen in Germany, they developed these incredibly precise new lab procedures.
Better measurements.
Much better. They could measure the isotopic composition of the ruthenium with amazing accuracy.
Isotopes, different versions of the element, slightly different weights.
Exactly. Think of them like atomic fingerprints. Different formation conditions, different locations in the early Earth might leave slightly different mixes of these isotopes.
So like a chemical signature, telling you where it came from.
Pretty much, yeah. And what they found was, wow, the isotopic fingerprint, the specific mix of ruthenium isotopes in some of these volcanic samples, it was different.
Different from normal mantle ruthenium.
Subtly, but measurably different. And crucially, That different signature matched what scientists predict the signature of ruthenium in the core should look like, based on how we think the core formed.
No way. So a tiny difference in atomic weight in a volcanic rock points all the way back to the Earth's core, formed billions of years ago.
That's the inference, yes. It was the smoking gun. You can imagine the excitement.
I bet.
Nils Messling, he was the first author on the study. He put it perfectly. He said, when the first results came in, we realized that we had literally struck gold.
Nice.
Our data confirmed that material from the core, including gold and other precious metals, is leaking into the Earth's mantle above.
Struck gold indeed.
Yeah.
Metaphorically and I guess kind of literally in the long run. Okay, so we have core material with this unique ruthenium signature getting into the deepest part of the mantle. But that's still hundreds of miles down. How does it get the rest of the way? Up to a volcano?
Right. So the research connects this finding to another major geological concept, mantle plumes.
These giant upwellings of hot rock.
Exactly. Theorized columns of superheated, buoyant rock rising from deep within the Earth. Maybe, just maybe, originating right near that core mantle boundary.
Okay.
The idea is that this core material, once it leaks into the mantle, gets caught up and trained in these rising plumes.
So the plumes act like elevators, bringing this deep material, including the stuff with the core signature, all the way up towards the surface.
That's the proposed mechanism, yes, an elevator from the depths. And when these plumes get near the surface...
They melt, cause volcanism,
yeah,
and build things like Hawaii.
Precisely. The study argues that the formation of these big oceanic island chains is a primary way this core-derived material actually makes it out onto the surface.
Wow.
Matthias Wilbold, another author, really drove home the scale of this. He said something like, our findings not only show that the Earth's core is not as isolated as previously assumed, which is big enough.
Yeah.
We can now also prove that huge volumes of superheated mantle material, several hundreds of quadrillion metric tons of rock, originate at the core mantle boundary and rise to the Earth's surface to form ocean islands like Hawaii.
Hundreds of quadrillions of tons. I can't even picture that number. It just sounds enormous.
It's vast.
So this isn't just some tiny academic leak. It's linked to these massive geological processes moving staggering amounts of rock over geological time, from the core boundary all the way to, well, a Hawaiian beach eventually.
It fundamentally changes the picture, doesn't it? Tells you the Earth isn't just neat, separate layers.
Yeah.
It's dynamic. There's exchange happening connecting the deepest interior to the surface.
Yeah. That subtle isotopic fingerprint in a rock really unlocks this view of a process on an absolutely immense scale.
It really does. So for you, the listener, it's not just, oh, cool, maybe some gold is leaking out, although that is cool.
It is pretty cool.
But the bigger takeaway is about Earth's whole internal plumbing system, how it works.
Right. So implications. It breaks the idea of the core being totally isolated.
Check.
It gives strong evidence for these massive mantle plumes actually starting way down at the core mantle boundary.
Double check. It supports that model.
And it connects those deep processes directly to surface features we can see, like oceanic islands.
Which fits into broader theories like plate tectonics, right? Absolutely. It helps affirm that part of the plate tectonic model involving deep mantle sources for some volcanism. And, it forces us to think again about how the Earth evolved, how the core and mantle differentiated, how elements got distributed over billions of years.
So is this leaking still happening? Is core material still riding these plumes up today?
Well, the fact they found this signature in relatively young volcanic rocks strongly suggests, yes, it's an ongoing process.
Wow.
A slow, perhaps continuous exchange over millions, maybe billions of years, potentially, slowly adding to the inventory of these precious metals near the surface.
But that raises another question, doesn't it? The timeline.
Exactly. That's one of the big things researchers want to figure out next. Was it always like this?
Has it been leaking steadily for billions of years, or did it happen in bursts?
Right. Nils Messling mentioned this too. He said, whether these processes that we observe today have also been operating in the past remains to be proven.
Yeah.
Our findings open up an entirely new perspective on the evolution of the inner dynamics of our home planet. Understanding that history, constant drip or occasional flood, is key.
Yeah, that makes sense. So let's sum up the core idea then. This research paints a picture of a much more dynamic Earth than maybe we thought. Even the deepest part, the core, isn't sealed off.
Not completely.
It's interacting with the mantle, slowly sending material, including valuable metals, upwards. And this happens via these huge processes, mantle plumes, volcanism.
Yeah, it really shifts our perspective on how isolated the core is. And it gives real tangible support for these giant geological conveyor belts connecting the deepest Earth to the surface we inhabit.
It really feels like we've just cracked open a new window looking deep inside the planet. This study it opens up so much about Earth's history, its evolution, how it works now.
Mm-hmm.
And thinking about that timeline question, has this leak always been happening? What does that tell us about how the planet was in the past? Or how it might change in the future?
It's a fantastic reminder, isn't it? That even parts of our planet that seem utterly stable and unchanging, they're involved in these incredible slow-motion processes on scales that are just staggering. We're only just starting to really piece it all together.
Definitely gives you something new to think about next time you see pictures of Hawaii, right?
Yeah.
Maybe some of that sand started its journey near the center of the Earth.
It certainly could have. A long journey, but possible.